What does Japanese isolationism, eyeballs, and a 21st century power systems engineer have in common? Well, that's what we're about to find out today. We're going to be covering the eyeball theorem with the Sangaku expansion, presented by Hunter Maurer and me, Anna Wise. So what is the eyeball theorem? Well, the eyeball theorem states that for two disjoint circles with centers A and B, if the tangents from A intersect A at W and Y, as you see, and the tangents from B intersect at X and Z, then WY is equal to X and Z.
First, we need to prove the radius tangent theorem, which states that if xy is tangent to a circle A with radius AB, where B is on xy, then xy must be perpendicular to AB. First, we need to assume AB is not perpendicular to xy. If that's true, then there must be a C somewhere on xy such that AC is perpendicular to AB. Since in this case ACB is 90 degrees, then AB must be greater than AC. And we can see AC intersects the circle at D. Since AD is equal to AB, because they're both the radius, AC equals AD plus DC. And now our earlier statement that AB is greater than AB plus DC, it's now a contradiction. So we see that XY must be perpendicular to AB.
Now, before we jump into the eyeball theorem proof, we first have to prove the Pythagorean theorem. Suppose we have a right triangle with side lengths A, B, and C, where C is opposite the right angle. Then, A squared plus B squared equals C squared, the much well-known Pythagorean theorem. To go about proving this, first we take 3 copies of our triangle and position them into a square as shown. Since our triangle is right, the other 2 triangles are complementary. Since each corner of the inner quadrilateral is 180 degrees minus 90 degrees, it is a square. We can see that the total area K is the sum of the areas of the inner square and triangles. Therefore, the total area is equal to the area of the square plus the area of each of the triangles, and they all have the same area. We can therefore calculate the total area by just making a square, or saying A plus B, which is the length of each side, squared. And doing some algebra, we see that the area of the square is C squared. The area of each of the tiny triangles is 1/2 times AB, because of 1/2 base times height. So 4 times the area of each triangle is equal to 2AB. And substituting everything together, we get A squared plus B squared equals C squared. Okay, now that we've proven the necessary lemmas, let's move on back to the eyeball theorem. Let's first draw AB connecting the 2 circles. Then let's draw altitudes WU and XV onto AB. These altitudes come at a 90-degree angle to AB. Next, we will draw the radii AR and BQ. BR is perpendicular to AR and AQ to BQ by the radius tangent theorem that we just proved. Now, once we bring in some signs into this, let's look at angle alpha. Sine of alpha, when looking at triangle BQAB, is equal to BQ over AB, or opposite over hypotenuse, R2 over AB. And sine of alpha, when looking at the smaller triangle, AWU, is equal to W over AW. Similarly with sine of beta, you can see the rest follows through. Once we have the ratios and we substitute R1 and R2 where appropriate, we get these 2 ratios. When simplifying them down, we receive that R1 by R2 is equal to WU times AB, which is equal to XV times AB. Making them equal to each other, we see that XV times AB is equal to W times AB, or XV is equal to WU. However, we cannot yet say that YU and ZV are also equal. because we have not proven that they will hit the same points u while maintaining the right angle, allowing the signs to be used.
Now we'll need to drop altitudes yu prime and zv prime onto AB, which will of course be at right angles. And additionally, we'll know AT is perpendicular to BT and AS perpendicular to BS by radius tangent theorem. Now, we don't quite know yet that u prime and u and v prime and v are the same point, so we'll need to show that. In order to do so, we're first going to see that cosine of theta is equal to au prime over ay, which is equal to as over ab. And similarly for cosine alpha, we see au over ay is equal to aq over ab. So substituting these together, cosine of theta is equal to as over ab, which is equal to aq over ab, which is equal to cosine of alpha. This means that alpha must equal theta, so au over r1 equals au prime over r1. This means that au prime equals au, which implies that u and u prime must be the same point. We can see a similar process using phi in order to show bv prime is equal to bv. Since au is equal to au and aw is equal to ay, yu is equal to wu by Pythagorean theorem. And similarly, xv prime must equal zv. Since angle AUW and angle AUY are both 90 degrees, WY must be a straight line. So WU plus YU equals WY, and similarly XV plus ZV is equal to XZ. So finally putting everything together, we can see that WY must be equal to XZ, thus completing our proof.
Fantastic. So now that we've proven the eyeball theorem, we're going to do our expansion with Japanese Sangaku. But first, we're going to note an important contributor to this, Daotan Oi. Daotan Oi is a contemporary power systems engineer who is a well-known geometer and regularly contributes to geometric proofs. He proved the eyeball theorem using the result from a Japanese Sangaku, or geometric puzzle, and will be borrowing his logic to prove one case of that very puzzle using the eyeball theorem. So we'll reverse his proof to prove Japanese Sangaku. Alright, but what is Japanese Sangaku? Well, Japanese Sangaku states that if ABCD is a cyclic quadrilateral, then the incenters of triangle ABC, triangle BCD, triangle CDA, and triangle DAB form a rectangle, regardless of the cyclic quadrilateral's position.
So next we need to talk about circumcircles and angles. So to define a circle, we need 3 points. 2 points can define it in space, but its radius is not necessarily rigid. A third point will make the radius a rigid constant, and therefore we can have a singular circle. The triangle formed by these 3 points then is going to have this unique circle around its vertices, and we call this its circumcircle. Now we need to talk about some angles. So an angle in general represents the amount of a circle 2 lines subtend. We traditionally divide a circle into 360 degrees. So an angle from the center of a circle, a central angle, is going to be the same measure as the arc it subtends. And if we move the angle to the edge of the circle, it's an inscribed angle, which are half of the central angle of the same arc. So if a triangle is right, that right angle is inscribed in its circumcircle, which means the arc it subtends is half the circle, so the hypotenuse must also be a diameter of that circumcircle.
Okay, so I mentioned incenters when I was describing whatever Japanese Sangaku was, but what is that? Well, an incenter is simply the coincidence of all 3 angle bisectors. So let's find out what an angle bisector really is. Let's take an angle, ABC, with an angle bisector, BP. That is, it bisects the angle in half. Then drop two perpendicular lines from P onto AB and AC at Z and Y. These lines are the distance of P from A to C. Then angle PBA is equal to angle PBC. BP is equal to BP, since it's the same line. And angle PZB is equal to PYB, since they're both 90 degrees. So, both of these triangles, BZP and triangle BYP, are congruent by angle side. Therefore, PZ is equal to PY, and an angle bisector is the locus of all points equidistant from its sides. So, if we now complete this diagram and draw AC, we see we now have triangle ABC. We can make P the intersection of the angle bisectors of angle ACB and angle ABC, as two lines must always coincide at some point. Drawing PX like we did PZ and PY, we can see that PX is equal to PY is equal to PZ. So X, Y, and Z are equidistant from P. Therefore, since an angle bisector is the locus of all points equidistant from the two sides, then angle A's bisector must also land on P, which means there is a circle inside triangle ABC with tangents X, Y, and Z. We call the center of that circle P, the incenter.
Now we're going to prove this Sangaku expansion on our diagram of the eyeball theorem. We're going to have to show that RQST is a cyclic quadrilateral, and then we're going to show that its incenters form a rectangle. So triangle ABR, triangle ABQ, triangle ABT, and triangle ABS are all right triangles with the hypotenuse AB. So they must all have the same circumcircle with diameter AB, meaning RQSD is a cyclic quadrilateral. Next, we're going to need to show that WXZY is indeed a rectangle. So first, we know that WU is equal to XV, and the angles WUV and XVU are 90 degrees from the eyeball theorem. So we know that top half WXVU is a rectangle, and we can show the same thing with that bottom half YZVU, so we know the whole thing WXZY is a rectangle. Now let's take the triangle TRQ. This is one of our triangles we need to find the incenters of. So we know from earlier in the eyeball theorem beta equals phi, and both are inscribed, so the arcs AR and AT are equivalent. So since RQA and TQA are both inscribed, angle RQA must equal TQA. So AQ must be an angle bisector of angle RQT. Now, angle RAQ is equal to 1/2 arc RQ, which is equal to angle RTQ, since they're both inscribed angles on arc Q. Further, RAW is equal to arc RW, and since angle RTW inscribed, angle RTW is 1/2 of arc RW, which is 1/2 of the angle RAW. So we know that TW must be an angle bisector of angle RTQ, meaning W is the incenter of triangle TRQ. Similarly, X, Y, and Z must be incenters for their respective triangles. And so the incenters of the cyclic quadrilateral RQST form a rectangle.
Thank you so much for listening. We hope you learned something here. Thank you again for Hunter Maurer for handling the animations, and thank me for doing all the editing. And here are all the sources that we got all the eyeball theorem stuff from. And thank you, Dr. Akbar, and our Geometry Math 3321 class at the University of Texas at Dallas.